In these two problems, we're asked to simplify, right? So if you remember, simplify was a pretty open word. We were like, what do we have to simplify to, right? And I just said it would always say in the directions. Read the directions. Right? So for the purposes of this, I'm going to say no fractional exponents and no negative exponents, because that will give us a lot of practice with this. So let's see what we remember. So when you are multiplying and they have the same base, so like these both have a base of x, we're going to be adding the exponents, right? So I have 5 times 6 gives us 30. X to the power of, well, what's negative 1/2 plus 1/8? They don't have the same base, but I can change this to have a base of 8. So that would be negative 4/8. Oh, so that's negative 3/8, right? We're not going to rely on our calculator, hopefully. Negative 3/8. So let's get rid of that negative first, right? Because it says both pieces. It has a fractional exponent and a negative exponent. So let's get rid of that negative. If you remember, and we even talked about this with rational functions, if you have something like x to the power of negative 1, it's 1 over x, right? That's an inverse variation. So this is 30 over x to the power of 3/8. And now I've gotten rid of that negative, right? So the next thing that I want to look at is, how do I get rid of that fraction? Well, if you raise something to the 1/2 power, that's the same thing as taking the square root. If you raise something to the 1/3 power, that's the same thing as taking the third root. If you raise something to the 2/3 power, that's the same thing as taking the cube root of x squared, right? So the numerator is the power, the denominator is the radical, the root that you're taking. So this is going to be equivalent to 30 divided by the 8th root of x cubed. And that is how our answer is going to be left, based off of the directions I gave you, of no fractional exponents, no negative exponents. If you remember, and there was a practice worksheet that I linked the entire answer key to, that you guys had prior to us going out on this break. And that detailed answer key is posted on the Unit 7A supplemental materials if you want to go back and reference it. But sometimes the directions will say, like, it wants everything to be in the numerator, right? So it just kind of depends on that description. Okay, let's go ahead and let's take a look at this second one over here. So this is division. So I'm going to just start off, and I don't have to do this, but I want you guys to see it. I'm going to start off and I'm going to write this as a fraction so we can kind of talk about what we can do. So 9x to the 1/3 to the negative 3/2. So we're dividing by something that has a negative exponent. So I can take this entire thing and move it up to the numerator, and then it becomes a positive power, right? So I have 4x to the negative 1/2 cubed times 9x to the 1/3 to the positive 3/2. And now I no longer have that negative exponent there. Right? So the next piece of this that I want to do, and maybe I would have noticed that right away, and that's fine, is I want to actually distribute. Right? So that's going to give me 4 to the 3rd, which is 64, x to the power of negative 3/2 times 9 to the power of 3/2. What's that? 9 to the power of 3/2. You can kind of link it over here. What did we do? Well, we said that's the same thing as the square root of 9 cubed. 9 cubes. I don't know what that is in my head, but I do know what the square root of 9 is in my head. That's 3. So that's the order I'm going to do it in. 3 cubed. Oh, that's 27. Right? So then I've got 27. X to the, what's 3/2 times 1/3? That's 3/6 or 1/2. Right? Now it looks really similar to this first one we started with. So what is 64 times 27? That's 1728. So 1728. X to the power of negative 3/2 plus 1/2 is -2/2, right? You're going right on a number line. -2/2 is just -1. And then we talked about that over here too, right? I can just move that, and we talked about this with rational functions. I can just move that to the denominator, divided by x, and that is my answer. I don't need to say that it's x to the first power. Fantastic, right? So let's refresh our memory on some of these properties. In today's lesson, we're going to be building a little bit on these properties, right? So we're going to use, we first have to define what a logarithm is. Some of us may have heard of it, but we do need a solid understanding of what a log is. And then we are going to use what we already know about the properties of exponents. We will talk about properties of logs, and we're going to be simplifying expressions, right? And again, that's going to be like, what do the directions say? Like, are you simplifying to a single log? Like, that is often what it says, single log. That's often what you'll see, but sometimes you might be simplifying it to an actual number. You might be even seeing if it's possible to do, but we're not, like, there's no equal sign here. You're not solving anything, right? You're not going to say like x equals, yeah? So in order to get started, we're going to define what a log actually is. So logarithms, the definition of a logarithm. So log base b of a equals x if and only if. So this is if and only if, right? Meaning it's a definition. Like, it works both ways, right? So I could go either way here. Like, they're both, I could start with either one and translate it into the other. So log base b of a equals x if and only if b to the power of x equals a. So think about where those placements are, right? So this is called the base. This is called the argument. This is called the base. This is called the argument. Okay, base was a word that we had heard. Oh, that rhymed. Argument, maybe not as much, but if you look at this, the argument is the outcome. And then look where the argument is here, okay? This is, if you're not writing anything else down, I would just make sure that you have this stuff written. This is saying the argument must be greater than 0. The outcome of an exponent must be greater than 0. And if you take that back to what it looks like if you graph an exponential function, I'm going to graph it, and then I have a dotted line here. Oh, my asymptote. The parent function has an asymptote at y equals 0, right? The entire thing always happens above y equals 0, right? So the argument, the outcome of an exponent, will always be greater than 0. So think back to that, make sense of it. And then the base, this is your base or this is your base, is always going to be greater than 0. It has to be, right? That's your growth or decay factor. It can be a fraction, right? It can be between 0 and 1. We looked at that, and that was like when it decayed, right? But it's not going to equal to 1. What happens if your base was 1? So like, let's say you wanted to graph the function y equals 1 to the power of x. Let's say you plugged in -6, 1 to the -6, oh, that's 1. Let's say you plugged in 0, oh, that's 1. Let's say you plugged in 7, oh, that's 1. Let's say you plugged in 52, oh, that's also 1. So no matter what x value you put in, you get a horizontal line. This is just equivalent to 1. That's just the line y equals 1. So it's not a logarithmic function. It's not an exponential function if your base is 1. So base is going to be greater than 0, and it's not going to be equal to 1. And this will be an idea that comes up often. So the x, I would guess that maybe you already know this piece of it, is an exponent. That is the exponent, right? So like the outcome of a log is the exponent. Logs are exponents. We are going to want to be translating between the two. Like, you're often going to be asked to go between the two. Or if you're solving an exponential function, right? Like, we were always, prior to leaving, like, we were able to make them have the same base. Well, if you can't make them have the same base, that's when you turn to logs in order to solve them. So don't erase the things we already learned. Just let's add to it. So how I'm going to read this, and I'm going to do this over the next few slides. The exponent that turns B into A is x. The exponent that turns A into B is x. Okay, I'm going to be saying that. So let's look at translating between the two to solidify our understanding of it. So log base 5 of 25 is 2. The exponent that turns 5 into 25 is 2. So 5 squared is 25. Oh, that makes sense. The exponent that turns 2 into 32 is 5. So 2 to the 5th power is 32. Right? So let's see, make sure that it makes sense. The exponent that turns 1 half into 64 is negative 6. So 1 half to the power of negative 6 is 64, right? And we can even check these. Like, does that make sense to us? Is 5 squared 25? Yes, it is. Is 2 to the 5th 32? Yes, it is. Is 1 half to the negative 6 64? Well, this is the same thing as 2 to the 6th, which is 64. So yes, it is. Let's look at solving for the log. So this is like solving for the exponent. Solving for the log, which is solving for the exponent. Okay, so log base 5 of 25 is x. The exponent that turns 5 into 25 is x. So 5 to the power of x equals 25, right? Even though you might be looking at this and you know what x is, like you know exactly what it is because this is one you've worked with, let's use some of the things we've talked about and let's rewrite this so that they have the same base. How can you rewrite 25 to have a base of 5? Well, 5 squared. We can then use the ignore property, and x must be equal to 2. Sorry. Right, so let's do the same thing on the next one. The exponent that turns 2 into 32 is x. Right, so this is going to give us 2 to the power of x is 32. Can we rewrite it so they have the same base? 2 to the power of x equals 2 to the power of 5. Ignore the bases, so x must equal to 5. So this was 2. This was 5. I had a teacher in high school, I think in high school, that when we would write these and you had to turn a log into an exponent, you start with the base and you like go around and it becomes an E. I don't know, it's stuck. If it works for you, use it. What about this last one? The exponent that turns 1 half into 64 is x. Right, so that's going to mean 1 half to the power of x equals 64. So let's rewrite these. This is the same thing as 2 to the negative first to the x, which I can just say 2 to the negative x equals 2 to the power of 6. 2 to the power of 6. So I can ignore their bases. Negative x must equal to 6. So x must equal to 6. Right, so 1 half. Oh no, I'm sorry. X must equal to negative 6. Right, so 1 half to the power of negative 6 equals 64. That makes sense. Right, so this x must be negative 6. This x is 5. This x is 2. So now we're going to look at solving for the argument. So we did solving for the log. Now we're going to solve for the exponent. The argument. The exponent that turns 3 into x is 2. So translated, 3 squared is x. Oh, we know that. So 3 squared is 9, right? So your argument is 9. What about here? The exponent that turns 7 into x is negative 2. 7 to the power of negative 2 equals x. That's 1 over 7 squared, which is 1 over 49. So x is 1 over 49. So this was 9. This is 1 over 49. Oops, sorry. The exponent that turns 1 half into negative 4 What is the exponent that turns 1/2? I'm sorry. I said that totally wrong. What is the exponent that turns 1/2 into x? -4. I'm still saying it wrong. The exponent that turns 1/2 into x is -4. The exponent that turns 1/2 into x is -4. It's a negative exponent, so let's flip these to make it positive. So this is 2 to the 4th. 2 to the 4th is 2 times 2 is 4, times 2 is 8, times 2 is 16. So this is 16. Fantastic. Okay. So the last thing that we have to look at, we did solving for the log, or the exponent, solving for the base. And now, I'm sorry, solving for the argument. Now we're going to do solving for the base. So the exponent that turns x into 25 is 2. So x squared equals 25. Right? We want it to be an x to the first power. So x squared, we can raise it to the 1/2 power. As long as we're doing it to both sides, you're allowed to do it. That's legal math. Some of you guys might be thinking like, oh, I know 1/2 is the same thing as taking the square root. Great, it is. Do that as well. Oops, sorry, too fast. Right, so this then indicates to us that we have 5 is our answer. I wish I could hear from you guys. Like, are we missing something? Is there another answer? Does this cause any confusion? Maybe we're thinking, well, isn't x plus or minus 5, right? You always told us that when we're the first ones to draw that square root symbol, you get plus or minus 5. If we were to graph these two, you would have x squared, and then you would have this line, y equals 25, and you would have 2 points of intersection. One would be 5, and one would be -5. Why are we throwing out that -5? Well, why are we? Like, what was the definition of a log, right? What was that thing? I squared it at the bottom a few slides ago and said, if you're not writing anything down, write this down at least, right? So the base has to be greater than 0. Right? If it can't be -5, -5 is not possible because it does not fit the definition of a logarithmic function. The base must be greater than 0. So always remember, like, does it actually fit the definition? Like, look back and see, does it make sense? Right? What about this one? X to the power of 5 is 1/32, because I could read this as the exponent that turns x into 1/32 is 5. So, just write it right here. X to the 5th power is 1/32. Well, I'm going to raise both sides to the 1/5 power, or take the 5th root. And that's going to give me x equals 1 over, what is the 5th root of 32? 1/2. Does that fit the definition? Yes. That is acceptable. Your base can be 1/2. 1/2 to the 5th power is 1/32, right? Like, you're going to raise both parts, the numerator and denominator, to the 5th power. What about this last one? The exponent that turns x into 1 is 4. So x to the power of 4 equals 1. Raise both sides to the 1/4 power. This is going great. X equals 1. Great. No, not great. What's wrong with this? Can your base be equal to 1? We talked about how this isn't going to work, right? So 1 to the 4th, like, this could be any number. 1 to the 3rd power could be 1. 1 to the 2nd power could be 1. It's not possible, right? So b cannot equal to 1, so this has no solution. I'm going to say the empty set. None. It's not possible. Your base cannot be 1. So we kind of looked at these, but I just want to look at a little bit closer at what's happening with the definitions, right? So here we have a negative base. what happens when we have that negative base. Right, so the exponent that turns negative 4 into x is 1/2. So negative 4 to the 1/2 power is x. That's the same thing as taking the square root. Well, what's the square root of negative 4, right? That's an imaginary number, which stops us. Right, so this is not possible. Your base must be greater than 0. What about here? The exponent that turns 4 into 0 is x. This is saying 4 to the power of x equals 0. Well, 4 to the power of x, doesn't that have an asymptote at 0? If you were to graph it, this is y equals 0. That's never going to be true. There is no, I can't change 0 to have a base of 4. 4 to no power is ever going to give me 0. Right? So your argument must be greater than 0. And we just did this one, but 1 to the power of x equals 2. Well, this is just going to be a horizontal line at y equals 1. This is just going to be a horizontal line at y equals 2. They're literally never going to intersect. Right? Your base cannot equal to 1. Right? So these are the really important pieces of this definition to uphold. Right? So whether you're solving for the base, the argument, any of that, but these are the pieces we want to know. So just to summarize what we just went through and what we just tried to solidify was in the expression log base b of a, b is called the base and must be greater than 0 and not equal to 1. A is called the argument and must be greater than 0. And the answer to a log expression is an exponent. So let's look at a little bit closer at some of the actual properties. Now that we've defined it, let's look at these properties. And there's going to be a lot of similarities with exponents. So log base b of x plus log base b of y. When you're adding the sum of two logs when they have the same base, we are going to be multiplying their arguments. So this is going to give us log base b of x times y, right? Hopefully that looks familiar, right? Like when you were multiplying, right? If I had x squared times x to the third, I would add, and this would be 2 plus 3. So think about some of the similarities there. Oh, this was the opposite. They have the same base. I'm adding, and now I'm going to be multiplying their arguments. So where does that leave us for number 2? I'm now subtracting, and they have the same base. So I'm going to divide their arguments. Right? When we divided, and you would x to the third divided by x squared, you would subtract their exponents. Oh, it's the opposite. Number 3 is called the bring down property. Or I guess up property. So I now have my argument is being raised to a power. It's not the entire log, just the argument. So I'm going to take the exponent and I can actually bring it out in front as a multiplier. So this is equivalent to n times log base b of x. So if I was going to do an example of that, so let's say I did log base, I can't think of one now. Nine. I'm just going to do this. Right? So if I wanted you to simplify this for me, and I want you to tell me what is the log equal to, you would say 9 to some power has to equal 9 squared, and you would get 2 as your answer. Right? So I can also think about it, well, what if I brought that 2 out in front as a multiplier, right? And then I did 2 log base 9 of 9. Well, what is log base 9 of 9? 9 to what power is 9? 1. What's 2 times 1? Oh, also 2. Right, so that's where that rule is always going to work, right? So there's my example. I kind of answered number 4 then, right? So what is the exponent that turns b into b? I just answered it right here. If your base and your argument are the same, so base equals argument, it's going to give you 1. A few more properties. So log base b of b to the power of x I also just did one just like this, didn't I? So I'll use the bring down property again, but you might not need it. So I'll bring down the x. Whoa, x times log base b of b. Well, what is log base b of b? 1. X times 1, you just get x. So it's if the base and the argument are the same, it's almost like they cancel, and I just end up with this exponent. The power of the argument. I'm going to actually we're going to do more with this one on the next slide. So I was going to say hold off on the questions, but it's not like I can hear your questions right now anyways, but we are going to be doing more of this later. So this is called the change of base, which sometimes in order for properties to work, we need the base to be the same in order to kind of see what happens. And then sometimes even just to work with our calculators, we need the base to be the same. Or we need a certain base. So I could change the base to be anything. So what you're going to be doing is, so this is going to be equivalent to log of x over log of b. And now I have 2 logs that have the same base. You don't know what the base is yet. The base is actually 10. That's what this one is. So that's called the common log. If you don't see a base, the base is 10. So this is equivalent to log base 10 of x. So if you have looked at your calculator yet, not that we need them quite yet, but if you're looking at your calculator and you say the log button, that indicates that it's log base 10. What's interesting is if you push second log, it's going to give you 10 to the power of x, which should give you a hint as to, oh, it's the base of 10. So if you're ever forgetting that. So I could change this base to anything. Like I could have written, oh, just kidding, I want this to be log base c of x over log base c of b. And that value could be anything. Okay, so you can change the base to be absolutely anything, but it's log of the argument over the original base. This right here is called the natural log, which is log base e. So if you see ln, that's also in your calculator, right? That's right below the log button. And if you push second ln, you actually end up with e to the power of x, or e to the power of whatever you want it to be, which should remind you of that. So e, and there was a little bit with it on the last objective on the supplemental materials, but e is used when you're doing like growth models and like compound interest and compound continuously. And what it's saying, and there are 2 videos that I thought were pretty good on that supplemental material if you want to go back and watch them. But what it's really getting at is like, if I invest $1 into the bank, the more often I compound it, it's going to approach this number that is like 2.71, and it keeps going. It's irrational, and which is E, right? So if I compound it continuously, like if I start by compounding it monthly and then daily and then every minute and then every second, you're going to get like, you're not going to notice a huge difference, but it's going to, as you get compound more often, which is compounding continuously, you're going to approach that value. If you're just looking at it as in like, I invest $1. So it comes up with compounding. And it's Euler's number. It's an irrational number. It's kind of like pi, it's just not as commonly used or as commonly known as pi. So as I just said, I want to talk more about the change of base formula to prove it. So we're going to start with log base a of y. And we generally, if you've got the change of base, we know we want to end up with log of y over log of a. Whatever that base is, I don't know. Maybe I'll say it's c. or b, or whatever it is. Okay, so the first thing that we're going to do with this is we're going to change it to an exponent, right? Because it's the exponent that turns a into y is x. So we can do the same thing to both sides. I'm going to take the log of both sides. I'll take the log base of b. It doesn't matter what the log base is. I can use the bring down property now to bring this x down, right? And then how do you get x by itself? Ooh, that was an interesting square rectangle thing. I'm going to divide both sides by log base b of a. It's going to cancel, and I'm going to be left with x equals log base b of y divided by log base b of a. Oh, isn't that what I wanted to end up with? That is the change of base formula. You can come up with that. You don't have to memorize that. That's something that you can always come up with, right? You can always be like, well, I want to solve this. I want to change the base. How can I do that? And you can come up with how you do it. That's a proof of it. Hopefully that brings a little bit of clarity. A few more things with logs, so kind of application of the change of base. I'm going to do it with proving 2 logs. I don't know that I'm going to do it with proving 3 or the product of 3, but it's the same idea. So let's say we've got this, and we're going to use the change of base formula to simplify. So we're going to look for a pattern. This is going to be log of b divided by log of a times log of c divided by log of b. Oh, look, these are going to cancel. And I'm going to be left with log of c divided by log of a, which is log of the argument divided by log of the base. Oh, interesting. Look at that. So what happened? I had my argument and my base when I was multiplying ended up canceling. And I just have log of a, log base a of c, right? So look at that pattern that happens there in order to do this. And you don't have to have that pattern memorized, but if you have it appropriately lined up, things will cancel, right? So here, I'm going to get, these are going to end up canceling. Oh, look, these are going to end up canceling. So I'm going to end up with what? Log base a of d. Right? And if that didn't work for you, you could write it out as log of b divided by log of a times log of c divided by log of b. Oh, look, cancel. Times log of d divided by log, oh, I spelled log wrong, of c. Oh, those cancel. So I'm going to just be left with log of d divided by log of a. Oh my God, I don't know what I'm doing wrong. Log of a, which is log of the argument divided by log of the base. Oh. The pattern just makes it go a little bit quicker. The last one we're going to look at is reciprocal logs. So log base a of b. So let's say like this was a 2 and this was an 8. The reciprocal of that, like 1 over, is going to be, this is going to be equivalent to saying 1 over log base b of a. So like the base and the argument switch, because it's like instead of raising something to the 3rd power, you want to take the cube root of it. So it's like you want to go the inverse way, because if this is 3, I want this to be 1 over 1/3. Right, so the argument and the base will switch. So let's look at some simplifying. Oh, this is a little bit more on natural log, sorry. So E is about this value, it keeps going, it's irrational, it doesn't continue to repeat. It's represented by E, but about 2.71, 2.72, that idea. Okay, so we're going to write it as 1 in log expression. Can we read it? Does it have the same base? Can you bring anything up or down? Can you move anything? And we are going to simplify, and we don't want to make up any properties as we're doing it. So let's see. Log base 3 of 2 plus log base 3 of 6 minus log base 3 of 7. So I can multiply. 2 times 6 is 12. And then divide by 7. That's all I can do. Fantastic. What about here? Log base 4 of 30 plus log base 4 of 49 minus log base 4 of 42. Log base 4 of 30 times 49 divided by 42. I think that's 35. Right, so what I did was 30 times 49, multiplied those two, divided by 42. I'm going left to right. What about here? Log, oh, what's the base? Base 10, it's the common base. So 50 times 10 divided by 5. That's 2, so it's 100. Log of 100. Even though it says to simplify to 1 log, and I have that, I actually know the answer of this, right? Because this is log base 10 of 100. So what is the exponent that turns 10 into 100? 2. If you can get a numerical answer, please get a numerical answer. Ooh, what about this? Let's see. Log base 7 of 3 plus log base 7 of 25. Where'd that 25 come from? I brought the 2 up as 5 squared. And then I can multiply their arguments because I'm adding log base 7 of 75. I can't get a numerical answer to that. 7 to no power is going to give me 75. So what we're going to do now is we're going to actually, and this is the supplemental worksheet, I'm going to go through it, but I really encourage you, if you're like, hey, I want to check my own understanding, like print this or just like pause the video and try 2 at a time, right? If you're not comfortable, maybe watch me do 2 of them, and then you pause it. But I really would love to see, or I think it'd be a good idea for you to kind of see where are you with it. So I can do this first one in 2 ways. So this should look familiar because this was product of logs. Nothing is the same base, right? So I could use the change of base formula. Or I could line these up, right? So if my argument and my following base match, things are going to start to cancel. So let's see. Let me just write down log base 5 of 2. So I would want log base 2 of 27 to come here. Right, so those would then cancel. Is there something that has an argument of 5? Yeah. Log base 7 of 5. Is there something that has an argument of 7? Yeah. Log base 3 of 7. So based off of that pattern we just saw, these will cancel. Oh, these will cancel. Oh, and these will cancel. So I'll end up with log base 3 of 27, which is just 3, because 3 cubed is 27. If that's not something you recognize, write it out for yourself and say, okay, log of 5 over log of 7 times log of 7 over log of 3, and I cancel as I go, times log of 27 over log of 2 times log of 2 divided by log of 5, right? Oh, these are going to cancel. Oh, these are going to cancel. So you're going to be left with log of 27 over log of 3, which is log of the argument over log of the base, which is still going to give you 3, right? So there's multiple ways to go about doing that. What about the second one? It's almost like you're doing composition. So I'm going to start from the inside. Log base 2 of 32, well, 2 to the 5th power is 32. And then you're going to do log base 5 of that. 5 to what power is 5? Oh, well, 1. So then you're going to do log base 9 of 1, which is 9 to what power is 1? Oh, 0. So you're going to do log base 12 of 0. 12 to what power is 0? Not possible, right? Those will never intersect. That's not true because the argument must be greater than 0, right? So there's no solution. Fantastic. Okay. All right, let's do same idea. And again, I encourage you to pause it and try it on your own. Log base 4 of 64. 4 to what power is 64? 3. Log base 3 of 3. 3 to what power is 3? Oh, 1. Log base 2 of 1. 2 to what power is 1? Oh, 0. That's our answer. We don't We went through all of them. Okay, this one is cool. Let's try to recognize some patterns here. Let's start with that exponent. Log base 7 of 243. What is 7 to the 343rd power? 3. Right, so that whole thing is just 3. I can bring this 3 out front, and I've got 3 times log base 7 of 7. This should look like a property we had. Well, 7 to what power is 7? 1, right? So you've got 3 times 1, which is just 3. Ooh, that was interesting. Right, so if we looked back at this a little bit, I really ended up with just this exponent, right? So like so many things ended up just canceling because you were doing inverse operations. It's like I just ended up with the exponent. I was doing things that were inverse of each other. Like I did 7 to the, like if I look at just this piece of it, just that piece is 343. Oh, look, the 7 and the log base 7 actually just canceled. So 7 to the power of log base 7 of 343 is just 343. They're inverse operations of each other, which is going to allow us to kind of do this one. How can I make that one kind of look like this? Like I need these bases, the base of the log and the base of the exponent, to be the same. Because I can't do 2 to no power is 5. That's not a nice one. So let's change 4 to have a base of 2. Well, that's, whoa. 2 squared, sorry. Times log base 2 of 5. What can I do with this? Oh, I can bring that up. So that's 2 to the power of log base 2 of 25. And then again, these are inverse operations. I'm just going to end up with a 25 there. Great. All right, a few more. Again, if you haven't paused the video to try any, please try some. For this one, I'm going to write it as log base 7 of 8 divided by log base 7 of 1/8. And then let's get rid of that fraction. So log base 7 of 8 divided by log base 7 of 8 to the power of -1. Well, what can I do with this? When I'm raising something, when I'm raising an argument to a power, I have the ability to bring it out in front as a multiplier. So let's go ahead and do that. Log base 7 of 8 divided by -1 times log base 7 of 8. Oh, look at that. Those cancel because they divide and equal 1. So you just end up with -1. What about this one? This one's cool. I'm going to bring both of these up. It's just my first thought. I'm not saying that's the only thing you can do. So this is that what I wanted to do? Yeah. 1 over 3 to the 4th power. Actually, no, I don't want to do that. What's going to be easier? Don't I know what this is? Log base 3 of 1/3. 3 to what power is 1/3? -1. Plus 2, and let's look at this. Let's look at what happens. So this is saying 27 to some power equals 9. Let's change them to both have a base of 3. 3 to the 3x equals 3 squared. 3x equals 2, so x would have to be equal to 2/3. Let's use what we already know, right? So this is going to be 2/3. So you've got -4 plus 4/3. -4 I can write as -12/3 plus 4/3. So my answer will be -8/3. There's definitely other ways to do this. Like I could have brought it up and I almost did that, but then I saw it to be more complicated for myself. I could have easily changed this 9 to be a 3 squared and then brought down the 2 and it would become a 4. Sorry, I just made this real messy. And then said like 2 to the 1/3 power. Oh, 4 times 1/3. Still 4/3, right? So there are different ways to go about this. And if you want to challenge yourself or like you wanted to try it a different way or you did it a different way and you got -8/3, you're good. Great. Okay, last few. Let's see what happens here. So log base 27 of 32 plus log base 27 of 1/4. I'm going to go ahead and multiply those. Right, so log base 27 of 8. And I'm multiplying it by log base 2 of 9. Ooh, this is like product of logs, and I don't see anything that cancels. Let's go ahead and use the change of base. Log of 8 over log of 27 times log of 9 over log of 2. Can I change some stuff? Yeah, right? So I can change log of 8. 8 is the same thing as 2 to the 3rd. And then I can bring that 3 out in front. So 3 times log of 2. 27 is the same thing as 3 cubed, and then I can bring that 3 out front. 3 log 3. What's 9 the same thing as? 3 squared, and I can bring the 2 out front. 2 log 3 divided by log 2. And then things will cancel. Oh, look at that. Right? And I end up, oh, even those 3's cancel, and I just end up with 2. What about number 9? I don't really know what I can do with the numerator. 2 to what power is -8? Oh, wait. I know the definition really well, and the argument must be greater than 0. So there is no solution to this. This is not possible. No answer. The argument must be greater than 0. Know the definition. Please. Okay, so this last one is really neat. So I'm going to tell you, you're going to probably use a calculator at some point for this, but we want to do this without using the log button in our calculator, which we really haven't done at all. So what I've done is I provided you an estimation of log of 2, log of 3, and log of 7. What is the base for these? 10, because there's nothing there. So we're multiplying all these arguments. That means I could write this out of log 1 plus log 2 plus log 3 plus log 4, log 5, log 6, log 7, log 8. Oh my god, am I going to run out of room? Log 9. No, log 10. Right? And let's think through these. Well, what is the log of 1? The log of 1, I'm going to give myself a little bit of room. Log 1 is 10 to what power is 1? 0. So I'm going to cross them out as I get them. What about the log of 2? Oh, it tells me 0.301. What about the log of 3? Oh, it tells me 0.477. This is going well. Ooh, the log of 4. What's 4? That's just log of 2 squared, which is 2 log 2. So that's going to be 2 times the log of 2, which is 0.301. Log of 5? Ooh, I don't know that. But I could say that's log of 10 over 2, which is going to be the log of 10 minus the log of 2. What's the log of 10? 10 to what power is 10? 1 minus 0.301. What about the log of 6? Don't know that one either, but that's log of 2 plus log of 3. Right, because you'd multiply their arguments. So log of 2 is 0.301. Log of 3 is 0.477. I forgot to cross them out as I was going. What about the log of 7? Oh, it gives me that one, 0.845. That's on a nice product, so that's a prime number. Log of 8, that's log of 2 cubed, which is 3 times the log of 2. 3 times, what's the log of 2? We ran out of room. What about the log of 9? That's the log of 3 squared, which is going to be 2 log 3. It's a 3. The computer is getting a little interesting now. Log 3. And then the log of 10, we actually talked about this one. So 10 to what power is 10? That's just 1 if the base and the argument are the same, right? And then this is where I would want to use my calculator. And this would be an interesting one to go ahead and check. So I'm going to do 0 plus 0.301 plus 0.477 plus 2 times 0.301 plus 1 minus 0.301 plus 0.301 plus 0.477 plus 0.845 plus 3 times 0.301 plus 2 times 0.477 plus 1. I feel like I get a different answer every single time I do this one. 6.559 is what I'm getting. Hopefully that's right. If not, call me out at some point. And then it would be interesting because the base is 10, so that's the common log that's in my calculator. If I just did log of 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10, and I got approximately this, right? So don't call me out because I'm pretty sure I did it correctly. I get approximately this. Obviously, these are approximations. These are not rational numbers. So those were some quirky logs, right? They were some of them were pretty challenging. They made us think. But if you were able to do some on your own and follow along with my explanations, you're in a great place. So this is the end of this lesson. So we did a lot in this lesson. We defined a log. We used the properties, or we learned the properties of logs, and then we used them and kind of combined them with what we already knew about exponents in order to simplify, right? We did no solving here. We simplified a variety of log expressions. So thanks for watching. Feel free to go back and rewatch. I encourage you to do the Delta Math or any suggested homework in the textbook. Obviously nothing's required, but it's there for you, and I'm happy to answer any questions as we move forward. Thanks, guys.